Hello and welcome. You know that super complex phone in your pocket or the car you drive every day? Have you ever stopped to wonder how they get made with such perfect precision millions and millions of times over? Well, today we're going to pull back the curtain on the factory floor and dive into the unseen science, the surprising genius behind the modern assembly line. And believe me, it all kicks off with one really fascinating puzzle. So here it is. This is the big question, the central puzzle of all of modern manufacturing. Look, it's one thing to stamp out a million copies of the exact same product, and it's another thing entirely to build a single, one-off, highly customized car. But how in the world do you design a system that can do both, often at the same time, with just breathtaking speed and efficiency? That's the challenge we're going to unpack today. So where do you even start? Well, it all begins with the most fundamental choice of all, the physical shape of the production line. Yep, the actual geometry and layout of the factory floor. This one decision sets the stage for absolutely everything that follows, from speed and cost to how flexible you can be. And this right here perfectly captures one of the classic trade-offs. On one side, you've got the traditional straight line, the inline setup. This is the undisputed king of high-volume production for a single product. Why? Because the material flow is just dead simple, A to B to C. But the moment you try to introduce some variety, the whole thing just grinds to a halt. On the other hand, you have the clever U-shaped layout. It concentrates the whole work area, which means a single operator can easily manage multiple stations. This is fantastic for building different versions of a product, but as the research shows, there's a new variable. You now have to factor in the operator's walking time into your efficiency calculations. But this choice between a straight line and a U-shape is really just the beginning. It opens up a whole toolkit of different layouts. You've also got rotary machines for those incredibly high-speed, repetitive tasks. Think bottling plants, right? But the catch is they need super expensive, dedicated tools. And then there's what's next, modular cells. I want you to think of these like Lego blocks for the factory floor. They give you the absolute maximum flexibility to reconfigure your line on the fly. At the end of the day, there is no single best shape. It's all a strategic choice. What are you building for? Massive volume? Endless variety, or the ability to pivot in an instant? Okay, so we've got the physical shape locked down. But a factory isn't a static thing, right? It's alive with movement. So now we have to think about its rhythm, its pulse. The way things actually move down that line is just as critical as the path they follow. And here we go again with another huge choice. You've got continuous flow, which is kind of like a smoothly flowing river. The parts are always in motion, which is awesome for cutting down on idle time. But just try to imagine performing a really complex, precise task on a moving target. It's tough. Intermittent flow solves that problem. The line actually stops at each station, which allows a robot to do something very precise, very fast. The catch? Every single time you stop and start that quickly, you introduce vibration. And vibration is the enemy of precision work. So how do you deal with all that vibration? Well, the answer lies in a term from physics that sounds a little funny, jerk. In engineering, jerk isn't just a sudden movement. It's the rate of change of acceleration. Think about it like this. You know the difference between a smooth driver and someone who just stomps on the gas and then the brake? Or a super smooth high-speed elevator versus a clunky old one? That's jerk. By carefully controlling the jerk in a robot's motion, engineers can get it to move incredibly fast and then stop on a dime, all without causing those vibrations that would ruin its accuracy. It is the secret sauce to being both fast and stable. All right, we have our shape, we have our rhythm, but what are we actually putting together? On a modern line that builds a ton of variety, you could be dealing with thousands of unique components. So the next challenge is pure logistics. How do you get the exact right part to the exact right station at the exact right moment? The solution is this incredibly elegant idea called kitting. And honestly, this analogy nails it. It is exactly like a meal prep service, but for a factory. So instead of having these massive bins of every possible screw and bracket cluttering up the assembly line, you pre-package a neat little box, a kit that has every single part needed for one specific product. It's genius. And the benefits of doing this are just huge. I mean, right away, you get rid of so much clutter at the workstation. You also slash your energy use because you're not constantly hauling these giant pallets of parts all over the factory. But most importantly, kitting is what makes just-in-time production possible for assembly lines that are building a massive mix of different models. And it's only getting smarter, with new algorithms that are constantly optimizing schedules to find that perfect balance between having enough parts ready and the energy it costs to deliver them. Okay, so we've got the layout, the motion, the parts delivery, but who's the conductor of this whole complex orchestra? Well, that would be the factory's brain, the incredibly powerful software that schedules and optimizes every single action, every second of the day. I want you to think of this factory brain as having a toolkit full of specialized problem solvers. One algorithm might be like a grandmaster chess player, thinking 10 moves ahead to find the absolute perfect sequence of tasks. Another one might act like a logistics genius, figuring out how to get the most possible work done with, say, a limited number of robots. The main takeaway here is that these mathematical models are the invisible intelligence making thousands of perfect decisions every second to guide the entire system. And the impact of this factory brain is very, very real. The research shows that companies applying these models out in the real world are getting incredible results. We're talking about merging separate production lines, cutting down on the number of machines and stations they need, and significantly boosting their overall throughput. All of that leads to major cost savings. So the factory is fast, it's flexible, it's intelligently scheduled, but you know what? None of that matters if the product itself isn't perfect. And for today's technology, that means achieving a level of precision that is almost beyond human perception. It's gotta be flawless. What's really incredible is how engineers can now find flaws before a single part is even physically made. This process is kind of like digital fortune telling. They take the 3D design files, create this digital map of how every single component connects, and then they use advanced math to predict how tiny, microscopic imperfections in each part might stack up and cause a big problem in the final product. This lets them fix the design before it ever becomes a costly manufacturing mistake. Now, to get this level of perfection in the real world, the smart factory needs senses. It needs to see, using computer vision systems that can instantly recognize any part for any product. It needs to guide its human partners, using augmented reality to project digital instructions right onto the physical part someone is working on. And this is amazing. It needs to feel. Robots are now using force feedback and AI to gently sense when parts fit together perfectly, allowing them to do these delicate insertions with superhuman consistency. So here's the key takeaway. It's this. Sensing is the thing that unlocks true flexibility. You can have all the smart layouts and rhythms and algorithms in the world, but they're useless if the factory is blind, deaf, and numb. These senses are what allow the whole intelligent system to adapt to the real, imperfect world in real time. And this really gets to the heart of it all. As the research concludes, these advances aren't just about making things a little bit better. They are about fundamentally reinventing manufacturing. They are about creating the factory of the future, one that's more reliable, more flexible, and more intelligent than we ever thought possible. So, we've seen how factories are developing shapes and rhythms and brains and even senses. The entire system is getting smarter and more autonomous every single day, which leaves us with one last, really provocative question to think about. What happens when it no longer needs us at all?